Ready, set, go. Here we go. Maximum and minimum values. We are going to be talking about applications of derivatives. Uh, how do we use these derivatives really in a graphical context? Um, our next test will be over these type of topics, and they're all really related well together, except for there's one that really stands out. That's the mean value theorem, and a lot of people find that challenging. We're going to throw that towards the end of our unit, and so we're going to do things in a disjointed order, Okay, so we start with the idea of a critical number. A critical number of f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. So we'll see if you remember. Do you remember where a function is differentiable and where it's not differentiable? Can you think of a time where a function is not differentiable? At a corner, very good. If it's discontinuous, good. And if you have a vertical tangent, excellent. So as you look at this, we want to identify where there are critical points. And the first one is right here. This is a critical point because it's an endpoint. And at endpoints, f prime of c does not exist. And then in this situation, this is a critical point because f prime of c is equal to 0. Why is this a critical point? Yeah, it's a corner. F prime of c does not exist. How about this one? The derivative is 0. How about this one? F prime of c is equal to 0. And then this one, endpoint, derivative does not exist. Good. Are you able to look at a graph and identify where it is differentiable, where it's not? Hopefully you can. We like to consider the absolute maximum or global maximum of different graphs. We also like to consider absolute minimums. We like to consider local maximums and local minimums as well. So an absolute maximum in this situation, the largest value would be whatever f of c sub 4 would be. If you plug in c sub 4, that is the largest value that is produced by the graph. Would you all agree? And the absolute minimum would occur for what c value? Yep, f of c sub 1, that would be the smallest value. Now, the local maximums and local minimums, that happens wherever you have the largest or smallest values within an immediate area. And I know that that doesn't really sound like a definition that you may really like, but it's hard for me to really contextualize it another way. If you just kind of draw a small box around a region, wouldn't you agree that that's the largest value within that immediate area? Therefore, the derivative at fc sub 2 is a local maximum. And we have another spot that's a local maximum. Do you know what c value we would plug in to get a local maximum? C sub 4. So you can be a global or absolute maximum, but also a relative or local maximum. The terms that I'll use moving forward are absolute and local. I don't tend to use the words global and relative, but without a doubt, the AP exam may choose to use either or. And finally, the local minimums, f of c sub 3, again, the derivative isn't equal to 0, but it is the smallest value within that immediate area. And then also f of c sub 5, it's the smallest value in that immediate area as well. So it says, look at the graph provided, identify absolute maximum, minimum, as well as local minimax. We just did that right here. So Fermat came up with a theorem. Fermat was a great mathematician of a long time ago, and he said if f has a local maximum or minimum at C, and if f prime of C exists, then we know something is true. So I'm going to draw two different graphs, and you tell me which one Fermat is talking about. Here we have a value C sub 1. Here we have a value C sub 2. Here we have a value C sub 3. Here we have a value C sub 4. Look at his requirements. It says if f has a local maximum or minimum, would you agree that both these graphs have local maxes and local mins? And if f prime of C exists, which one, the one on the left or the right, has f prime of C existing? The one on the left. So we are only looking at both this one. So if that's true, then we can make a conjecture about those maxes or mins. What do you notice is true at the maxes or mins? What is equal to 0? The derivative. Yeah. The slope, the derivative, all the same thing. Then f prime of C is equal to 0. So let's just review what we talked about as critical points. So we examine critical points on a graph. This type of shape, those are critical points. As I consider this type of graph, I have another critical point. And within a vertical tangent, we talked about that, I have another critical point. Now, this isn't stated well, so I'm gonna write undefined but also discontinuous. If you have a graph that looks like this, then we would say it has a critical point as well because it's discontinuous. Some people say that this function would have a critical point, and we would disagree. It doesn't have a critical point if the point is not part of the original domain. Did everybody agree that whatever this x value was, that it would be eliminated from the domain? For example, the graph 1 over x squared. And what value is 1 over x squared? Undefined. 0. We don't say it has a critical point at 0 because 0 is not part of the original domain. However, 0 is still an important number to check out. So, the application. Let us find the critical numbers of the function. It's a polynomial. Everybody agree a polynomial is defined for all real numbers? And it's nice behaving. It doesn't have any corners, does it? So all we need to do is take the derivative and set it equal to 0. What is the derivative of this function? So if we set that equal to 0, we can factor it to 3x minus 1 and x minus 1. So therefore, x is equal to? What that tells us is that the function, it's defined for all those values, doesn't have any corners. It's going to have a local min or max at 1/3 and at 1. It tells us something useful about the graph. The next one, what rule would you have to use to find the derivative? Or you could just make it a lot easier. You could rewrite it as x minus 1 over x. Would everybody agree that those are the same? I would like to find the derivative of the second one as opposed to the first one, because the first one would use the quotient rule. The second one's a little bit easier. It's the same as x minus x to the negative 1 power. What's the derivative of x minus x to the negative 1 power? 1 plus 1 over x squared. So I'm going to set that equal to 0. Your first and immediate thought is to be able to take this and maybe subtract it over and cross multiply. Refrain from doing so. Create one fraction. If I want to create one fraction, what am I going to do? I'm going to find common denominators. So I have x squared over x squared plus 1 over x squared is equal to 0. Or x squared plus 1 over x squared is equal to 0. Yes. Okay, we'll try again. So if I have 2 plus 3 over 5, does everybody agree that that's the same as 2/5 plus 3/5? So we had x squared minus 1 over x, agreed? So x squared over x minus 1 over x, that's x minus 1 over x. Sorry for doing that too quickly. Okay. This is something you're going to do a few times. Important to think about. I look at it. Is it equal to 0 when the top is 0 or when the bottom is 0? When the top is 0. When the bottom is 0, it's undefined. Is the top ever equal to 0? No. Is the bottom ever equal to 0? At what value? At x equals 0. Is 0 part of the original domain? Could you plug 0 in at the beginning and get a value out? 0 is not part of the domain. So it's never equal to 0 on the top, and where it's equal to 0 on the bottom is not part of the original domain. So this has no critical values. Everybody agree that the absolute value of 3x minus 6 is the same as 3 times the absolute value of x minus 2? Could we graph that? What does that shape look like? V? So what x value would you have a critical value? At x equals 2. How come? Because that's where you have a corner. So x equals 2 is my critical value. The next one, a little bit more challenging. I would like you to think about this real quick. What's the domain of the square root of x? The domain, if you were to graph it, what does the domain of square root of x look like? Everybody agree 0 to infinity? Okay, so if we're looking for critical values, we're looking at any numbers that come up between 0 and infinity. Let's take the derivative. First, I'm going to rewrite it. F of x is equal to x to the 3/2 minus 2x to the 1/2. I added this problem as part of our notes not too long ago because I saw this problem on an AP exam, and I realized people were not prepared for it at all. Let's take the derivative. What do I get? 3/2 x to the 1/2 minus x to the negative 1/2, or 1 over x to the 1/2. Is everybody okay if I write that as 3x to the 1/2 over 2 minus 1 over x to the half. I want to figure out where that's equal to 0. Again, a lot of times people want to add it over and cross multiply. I encourage you to make one fraction. It's a better way to deal with it. If I want to make one fraction, how do I do that? Common denominators. What will I multiply top and bottom here by? X of 1/2. What will I multiply top and bottom here by? 2. What do I get here? 3x minus 2 over. Very good. Let's consider it. Where is it equal to 0 in the numerator? 2/3. Is 2/3 part of the domain? Yep. Where is it equal to 0 in the denominator? What would you plug in to get 0 in the denominator? 0. Is 0 part of the domain? It was, right? If you look at the original one, we got 0 to infinity, it's including 0. So it looks like that's where it has critical values. Take out your graphing calculator. I go into y equals, can somebody give me the equation for my function? It was the square root of x cubed, is that correct? I close that parentheses minus what? 2 roots of x. And if I zoom 6, it says that I should just be going from 0 to infinity. Does the function just go from 0 to infinity? It sure does. And furthermore, we should have critical values at 0 and at 2/3. If I zoom as a box, which is kind of my favorite application here, I press enter, I move down and over, and I'm going to look at my graph. Can somebody tell me, why do I have a critical value at 0? Because I have a endpoint. Why do I have a critical value at 2/3? The derivative is equal to 0. See how the calculus uncovers that hidden behavior that we had no idea that existed. That's the goal of our unit, is how to find those pieces residing within. We're going to pause. You're going to start a couple of these problems on your own. We now have ones that are a little bit more challenging. Please look at this example here. Is there any number you could plug in for t so that you would get 0 in the denominator? There is not. So the fact is that the domain for this one is all real numbers. Okay, so this is defined everywhere. Sometimes if you get something in the denominator, like, okay, that's going to be a problem. Maybe not. I want to take the derivative. I can't rewrite this like I did the other one, so I have to use what rule? The quotient rule. Derivative of the top, 1 times t squared plus 1 minus derivative of the bottom, 2t times t, all over t squared plus 1 quantity squared. So in the numerator, I have t squared plus 1 minus 2t squared. What is that going to give me? One minus t squared. So I have, if I t squared plus 1 minus 2t squared, it's going to give me 1 minus t squared over t squared plus 1 quantity squared. So we are wondering where that's either equal to 0 or where it is in fact undefined, where it does not have a value. Do you ever get 0 in the denominator? Is everybody convinced of that? Okay, so in the numerator, what values for t would give us 0? 1 or? How does the top factor? 1 minus 1 and 1 plus 1. So therefore, t is equal to plus or minus 1 Those are my critical values. If you looked at the graph would maybe produce something like this. You know, where you had local min and local max there, where it's defined everywhere. So kind of interesting. I want to find the critical points for F. What rule would I use there? I would use a chain rule. But first of all, folks, please identify this. What kind of a graph is this? Do you remember what a cubed root function looks like? Yeah, very good. It looks something like that. This one's going to be shifted over 3 units and reflected. So if you just think of the graph, where would you guess it has a critical point? What part of the graph would have a critical point? Wherever it goes straight up and down, right? Which will be at the shift of 3 units. Let's see if we can show that. I have u to the 1/3, and I have 3 minus x. What's the derivative of 3 minus x? And what is the derivative of u to the 1/3? Very good. 1 over 3u to the 2/3. So you can see your result is negative 1 over 3 times 3 minus x to the 2/3. Is the top ever equal to 0? No. Is the bottom ever equal to 0? Yes, at x equals 3. Is 3 part of the original domain? Yes, because the original domain is all real numbers. So at 3 is where this graph has a vertical tangent, and therefore the derivative is undefined at that spot. Do you remember what this graph looks like? A for the day, anybody remembers last year? X to the 2/3, it looks like the bird function. It is, yeah. So as you think about the Larry function, very good. Nicely played. So if you look at the graph, where would you guess it has a critical point? Would you agree at 0? Very good. So let's consider this graph then and show that that's the case. This is 1/4 x to the 2/3. Sometimes people use the quotient rule. Just write it as a constant of 1/4 out front. Makes the problem a lot easier. What's 2/3 times 1/4? 1/6 x to the negative 1/3, or 1 over 6x to the 1/3. Is the top ever equal to 0? No. Is the bottom ever equal to 0? For what value? X equals 0 is, in fact, where you have a critical point. And you should be able to think of the graph and say, yeah, I know I have a critical point because it's the bird function and it is a corner. See all the different examples we're trying to roll through? This last one, possibly a little bit more challenging. The domain of sine is all real numbers. The domain of cosine is all real numbers. So all numbers are in play here. Who can tell me what the derivative of sine of 2x is? Close, not cosine of 2x, but 2 cosine 2x. Why, Ashler? Yeah, you got to use the chain rule. So what's the derivative of cosine of 2x? 2 sine of 2x. I've got to figure out where that's equal to 0. I'm going to add the 2 sine of 2x over. I get 2 cosine of 2x equals 2 sine of 2x. What would you like to do now? Don't say divide by 2x. Divide by 2, okay. So we get cosine of 2x is equal to sine of 2x. What would you like to do now? We're going to divide both sides by cosine of 2x to get 1 is equal to tangent of 2x. We'll solve for this answer between 0 and 2 pi. Where is tangent equal to 1? Do you recall? We better inverse 1 on our calculator then, huh? My guess is you're going to need to be in degrees so you can understand the result. Anybody want inverse tangent in degrees to come up with the result? 45. Tangent is positive in the first quadrant as well as the third quadrant. 45 degrees, 45 degrees. So what are those two angles? 45 degrees and 225 degrees. But you know that we will ask for your answers to be expressed in radians. What is 45 degrees in radians? Pi over 4. So 2x is equal to pi over 4. And 2x is equal to what is 225 degrees in radians? 5 pi over 4. So if I divide both sides by 2, what is pi over 4 divided by 2? Pi over 8. And the next one will be 5 pi over 8. So I've given you an example about just about every single function that we can consider. The last thing I just want you to do is look at it again graphically to make sure we hit home. You guys tell me if I get to a critical number. That's it. How about here? Yeah. We would say that this would be critical if it was part of the domain. Is -3 part of the domain? So it's not a critical point. Those are your critical points. Okay, good job today. Last year, it appears that we took 2 days to do this lesson. We took 1 day today. So we're moving on to something new tomorrow. So I figured out a way to build in an extra day. So stay on top of this because we will be moving on tomorrow. It's only a day away.